Martin.
Thank you.
Okay, so I guess we can start.
Yeah, live stream is good to go. Konstantinos, you can start.
Yeah. So hey everyone, today the first talk is going to be delivered from Philip. Philip got his bachelor's in computer science in 2019. Then he joined industry for 3 years working as a software engineer, and now he's pursuing his master's in computer science in 3rd semester with a major in secure and reliable systems. And currently his main research interests lie in the areas of system programming and databases. So you can start, Philip.
Okay. Yeah, thanks for the introduction. And hi, everyone. So today we'll talk about continuous run ahead, which is a hardware optimization for memory-intensive workloads. This was published in Micro in 2016. Okay, so let's get into it. Some outline of the talk. We'll talk first about some background knowledge. Then I'll lay out the problem and the solution the paper proposes. We'll talk about how they try to implement this stuff. Then also what their observations are in terms of how it performs. Then I'll give some of my thoughts, and I'd like to hear some of yours on the pros and cons of the implementation and also the paper. And then we'll discuss a few points I thought were interesting in the end. Okay, so let's start. Yeah, some background. So this is very basic. Yeah, memory accessing. You have your cores that do the processing. You have a cache hierarchy, the memory controller over which the accesses to DRAM or main memory are done. So yeah, memory-intensive workloads try to have as many hits as possible, few misses. And yeah, for us, interesting is the positioning of the memory controller, so shared overall cores, and yeah, close to DRAM. So something a little more interesting are hardware prefetchers. These are units in hardware, like the name says, that try to execute data loads before they're actually used by the processor, so that once the processor needs the data, it's going to be a cache hit instead of a miss. So yeah, pretty much this. There's a few types of prefetchers you can discern between. Stream prefetchers, for example, just try to keep it going, right? You see kind of you've used these 10 addresses, so let's just load the 11th, 12th, and so on. Yeah, that's kind of the heuristic there. But you can do it a little more smartly, right? You can use like information about your cache misses to maybe deduce some more stuff about what you might need in the future. Right here, we call them global history buffers, the data structures that store this information. And yeah, you can do a bunch of stuff with this. So yeah. And there's many more. I show these because they're compared to a lot in this paper, and you see them in plots. That's basically it. So yeah, these prefetchers pretty much try to increase the hit rate, right? As I said on the previous slide. Okay, some more CPU kind of terms and optimizations. For one is out of order execution, which, as the name suggests, basically says that the CPU can execute instructions in any way it wants, or in any order it wants. Yeah, it can, if it has a slow, if it sees a slow latency operation, it can move stuff to the front that it has already its old source registers for, or something like that. But there's still the constraint that we do want to kind of have all the instructions take effect in program order. So for this, we have the reorder buffer. And yeah, it's basically like an assembly line, right? So you put stuff in, you take stuff out, and it gets executed in between. And so that it all comes out in order. Obviously, it's gonna be in order in the buffer, right? So yeah, a question that might arise is, or what happens if this buffer is full, right? It's in hardware, so it's limited in size. Well, it's not good. Obviously, if you have your buffer full and you encounter a low or a long latency operation, like a cache miss, we call the CPU stalled, right? So you can't make any progress. It can't do anything until this data is ready in this case. Yeah. So now run execution. This poses the question, well, can we use this time we spend in the stalling window to do something with the core, right? It's just sitting there not doing anything. And so proposed is to just keep executing, right? We don't want to commit these instructions. We don't want to save the results, if you will. But we will, crucially, we will find loads that will be executed in the future, and we will execute them insofar as they will be loaded to cache, right? So hopefully, once the normal execution resumes, those will be hits instead of misses. That's kind of the idea. Okay, so well, you might see that this basically does the same thing as a prefetcher, right? It tries to load things before they are needed. And the question then is, well, do we actually gain anything by this, right? Why would this be better than just the prefetcher, right? The prefetcher runs constantly. I don't think I said that, but the prefetcher is its own unit in hardware and runs all the time. So what does this give us on top of prefetcher? So yeah, maybe some of your ideas. Who has like an opinion on why this might still be worthwhile doing? Or it still has some benefits? Yeah, okay. Well, I guess it's not obvious. Well, the thing is, since we execute exactly the instruction stream, right? So exactly what will be executed by the normal execution once it resumes, we're much more accurate with our predictions, as is indicated by this plot here from the paper. So you have your the Runahead execution and two prefetches I was talking about. And yeah, quite clearly, well, maybe to explain a little, on the x-axis you have different benchmarks, memory-intensive benchmarks. And yeah, if you want to, like, for a big picture overview, the very right part is the mean of all benchmarks. And yeah, there you see clearly that it has quite a significantly better accuracy in what it prefetches. So accuracy kind of means how much of what we prefetch is actually used, right? How many, yeah, how effective is it? And yes, Runahead execution is better because it doesn't make as many assumptions. It doesn't have to make as many assumptions about what's going to happen because it knows a lot more. So it's less speculative in this sense. Okay, so back to our overview here. So this is all nice, right? This works well, you would assume. Well, there's still some problem with this, or we wouldn't still be publishing papers about it. And yes, the problem that the authors identified here is basically 2 points. You only execute it every now and then, right? It only happens when the buffer is full. You have this long latency operation, so you're limited when you actually access it, and also how long you access it, right? Because at some point the CPU can resume execution, and then you have to give it up. The CPU, that is. So yeah, the problem in general is Runahead execution is great, but we don't get to do it enough, really. But this is actually a practical problem as well, not just a conceptual one. Is also argued in the paper with a plot. Yeah, here we see the same benchmarks again. How much we actually prefetch from what we could prefetch, right? From what our kind of view would be, what would be possible to prefetch is the red bar, right? Which is, yeah, on average maybe 15, being generous. And the blue and the yellow bars kind of compare the possible performance gain over what we actually observe, right? So yeah, we're missing out is basically the point here, because we cover only yeah, a fraction of the misses we could. Okay, so well, as the title of the paper suggests, the solution is pretty intuitive. We just do it all the time. We keep doing Runahead all the time. We don't wait for a specific event to happen to start, and we don't stop at some other event. Yeah. So that's basically what the paper's about. Any questions up to here? Everything understandable so far? All right, great. Then let's keep going. How do they suggest this is done in practice? Well, I divided this into 3 parts, right? What do we execute? So instructions. And since we don't have the core anymore, right? We don't do it in a stall window only. We do it all the time. Where do we do it? Where's this hardware? And then what I call control here is just a few. It's just a kind of an umbrella term for yeah, some mechanisms to control what we execute. Okay. So first is instruction supply. What do we execute? Okay, so that's just this notion is not new of dependence chains, and are kind of to think about as a chain of instructions, kind of calculating the address really, and then culminating in the actual data load. And obviously, in our case, we are interested in loads that are misses. Right, otherwise, it's not really interesting to prefetch it. Yeah, so the interesting thing about these is that the insight is that these are, if one such dependence chain causes a cache miss at some point, it is likely to cause one again. It's kind of the reason why we use this here, why this is applicable here. And so, yeah, the obvious kind of solution is we just take such a chain and we run it continuously, we loop it. Yeah, so these chains, they have a few properties. They're usually short, like 20, maybe 30 micro-instructions, and simple. So usually integer, which makes sense, right? If you think about data access in your programs, maybe, right, it's usually I+1, basically, most of the time. So yeah, I marked here interesting. Obviously, there's many loads and many dependence chains, can bear multiple dependence chains for a load. So which dependence chain do we actually execute? This is kind of the second part of what we call here dependence chain selection. Yeah, so this is other paper that also does Runahead, and it does it, like I said, in the stalling window, and it just uses the chain for the stalling instruction. They call it original here, so that's why I called it original as well. So yeah, if you see original in the plot, that's that. But in this paper, they actually propose some new techniques, and for all of those, they kind of keep track of misses, right? They keep track of where they occur, how often they occur at that load, and also all the dependence chains that lead to it. And based on that information, you can make a decision what to execute. So yeah, they have these 3 policies. One is PC based. Yeah, use the chain of the last stalling PC. yeah, and use the chain that caused the most misses. Then the next one they call maximum misses is a little restrict or relaxed actually, in that it takes into account any PC, so any cache miss, and it uses the one that actually caused the most caches misses in the recorded history. And stall is similar, but it looks at the most stalls and not the most misses. Okay. So second point of implementation, hardware, where to execute this stuff. Well, there's kind of the obvious simple way of doing it in, an idle core, maybe some execution unit you already have, or an SMT thread. Yeah, and I would be interested in what you think are some pros and cons of doing it like this, right? Doing it in these places. Are there any ideas, thoughts? Yeah.
So I think the most obvious answer would be to use idle cores just to fill up the time or to reduce their idle time.
Yeah. Well, you think is it an often situation that you have idle cores?
Well, I don't know. I've never analyzed the idle time of my CPU.
Yeah, well, on yours, it's probably not that. It's probably like on a desktop computer, it's probably quite high, yeah. But if we're talking about memory-intensive workloads, maybe cloud computing and stuff, yeah, it's unclear how much idle time there is. But yes, it would very much depend on that. That's correct. Generally speaking, you're using hardware that could be used to execute, right? To make progress, basically, to do work, which is a downside. And also another more subtle, more subtle thing they mentioned in the paper is that this is like a full-blown core, right? It does way more than we need for dependency chain execution, right? It has like 8-way square roots of doubles, right? And we never need that for dependency chains, so it's over-provisioned, what they call it. Yes, but obviously it's easy to do, right? You have a lot of what you need. You have already in hardware. You have already there. Okay, but the authors didn't think this was good enough or promising, so they proposed a different approach, namely giving this its own space in hardware and its own engine, continuous Runahead engine they call it, and they put in the memory controller. Interestingly. Okay, so here's how they say this should look roundabout. So it really is like a small core, like a small execution unit inside the memory controller. Yeah, the most basic things are here, right? As it's ALUs that does integer operations, but because it doesn't need to do much more. It has a data cache, registers, also some input, right, where it gets the dependency chains. It even has some TLBs. So yeah, small, but still packs some functionality. Okay, who sees like some upsides to doing this, as other than the fact that kind of leaves main execution like by itself and it's like separate, especially maybe the fact that it sits in the memory controller. Why do you think that would be advantageous in this setting? Yeah.
I mean, one obvious benefit I can see is that we're very close to the memory, so we can basically Runahead will be much more effective at fetching memory or like blocks from DRAM
Yes, that's exactly one of the points. You're close to memory, right? To close to memory control, you don't need to go over the bus, right? The latency is a little shorter. So yeah, that's definitely not a bad thing. Yeah. Yeah, that's basically what I had in mind. Another a little subtle fact maybe is that it's automatically shared between cores, right? There's a bus going around from all cores to the memory controller. So you kind of just need to define some new signals or whatever, but the hardware is already there for a large part. Yeah, but obviously it is new hardware, right? You need to implement this, you need to design it, put it on a chip somewhere. Yes, and of course, where a prefetcher can maybe access L1, put things there, you can't do this from the memory controller, or not easily, if at all. Okay, so we have a space where to execute Runahead, this continuous Runahead. Let's go over some implementation details, maybe. So we have such a chain, we're executing it. Well, how long do we keep doing this, right? So the behavior is pretty simple, right? The CRE just takes whatever chain it gets, executes it, and once it gets a new chain, this is single core now, it gets a new chain, it just replaces the one it has, and it executes the new one. So really what the determining factor is the update interval from the core, right? How often the core gives out or sends a new dependence chain to the CRE. And we'll see this in the results, how this impacts the performance and accuracy. Yeah, this interval is usually measured in instructions executed of the core whose dependence chain we are executing, which is kind of a peculiar choice, but yeah, not sure why they did it this way, but they did. Yes. Another thing we can look at is, well, usually we have multi-cores, right? Multiple cores. So which core's dependence chain do we actually pick? So pretty straightforward policy here in the paper. Round robin is just everyone gets its execution window for some time, and then it's in the next one's guy's turn. Or we measure IPC, right? The kind of the instructions per cycle, how much work is the CPU actually getting done, and we take the one that has the worst, right, the least efficient, and we try to speed that guy up, help him out. Yeah, and yeah, this third policy basically keeps score. That's why I call it score. And the score is basically just how much the CPU is stalled, how often it is stalled. And the one that stalls the most is the one that gets our attention from the CRE, pretty much. So yeah. So interestingly, one of these three for dependence chain execution, or for which core to choose, one of these three is quite a bit worse than the other, and it's actually harmful in a way. And I was just wondering if maybe you have an idea of why that is, which one it is and why it is. It's not obvious, but maybe someone has, maybe I can just repeat it.
I'm guessing that round robin is probably not the best version, because if we assume we have a core that's never stalls, you will still do the thing, and it's useless for the core.
Well, just because it doesn't stall doesn't mean it's useless, right? You can still prefetch stuff. Just because there's a cache miss doesn't mean you stall the CPU, right? But yes, you could, well, with the information that I've given, you could probably argue that any is the worst, thinking about it. A round robin, for example, if you have idle cores, right, just a load running on one core, then the others really wouldn't do anything. Yeah. So, but that's actually not quite what I meant. It's hard to see. It's not really obvious at all. We'll see it in the results. I'll say it then. Okay. Yeah, so let's get to the results. So how are these results measured? Well, we use a simulator, x86 for single and quad core systems. So there's simulations for both. Yeah, put some stuff on here. Obviously, there's a lot more in the paper. For us, interesting, maybe there's cache L1 32 kilobytes. L2, which is actually the last layer, cache is 1 megabyte per core. ROBs 256 entries. And yes, about the benchmarks, they are from the set of benchmarks, the spec CPU 2006. And they restrict what they use to what they call memory intensive. So a lot of cache misses per instructions, basically, is the criteria. There's also the notion of heterogeneous and homogeneous workloads for multi-core simulations. It's pretty simple. Heterogeneous just means different workloads on all cores, and homogeneous means the four are the same. Okay, so performance. What do we get? What's the payout? So here we have a bunch of different setups. Pretty much, yeah. The interesting thing is really we have a bunch of prefetches and then also added CRE on top of it and compared the two scenarios. And as you can see, there's always a pretty decent speed up there. Yeah, so this is nice. Yeah, so this is IPC improvement, right? Since the instructions stay constant, higher just means fewer cycles. And we get a good, I mean, we can, for example, compare the light blue with the dark blue, right? That's just GSV and then GHB plus the continuous run ahead. And we get a good, what is this? 50%? Not quite. So it's pretty good. Yeah, so multi-core, okay, actually, yeah, right. This is pretty much what I said. Yeah, and crucially, this is not like negated by having a prefetcher. Yeah, they kind of, yeah, they do complement them. So maybe not complement, but they don't negate each other. So multi-core is here on the left. We have heterogeneous on the right, homogeneous workloads. Pretty much the same picture. Pretty nice, good speed up across the board, basically. So yeah, we saw that we get good numbers, good performance. But what does our CRE actually do? Like what's actually happening to give us this? We've seen this before, right? There's a lot of potential. This plot I showed earlier. And we can compare this to the situation now with continuous run ahead. We fetch actually a lot more. Like we get to a lot more work in time. So yeah, we go basically from, what is it, maybe 10% to around 70, right? So this is obviously drastically better. And also consistent with the performance improvements we saw on the previous slides. On these, also these things I discussed earlier, for example, here, dependence chain selection, so which dependence chain from a single core we take, like what policy we use to decide. There's some analysis in the paper on that. And yeah, the result is not too exciting. The stall policy is the best, but not by a huge margin. But yeah, that's also what they always use when they simulate. Another thing is the update interval. We talked about how often do we actually from a core send new dependency chains to execute. Here we have the performance and the mean performance and request accuracy. Yeah, as you can see, there's like a sweet spot between like 10K and 100K. And yes, why that is not too complicated. If the interval is too short, we run into the same issue again, that we don't get to do a lot of what we could, right? Same as before when the stall window was constrained. If the interval is too long, then we have a chain executing, but the CPU really moved on. It's not really interested in what we're prefetching anymore, so the accuracy drops as well for higher values. And this is also kind of the point why the IPC policy that I talked about for multi-chain, the multi-core selection policy, is actually really bad. Because, you know, if you think about it, a low IPC means if you wait for 100,000 instructions, for example, to execute, it's going to take more cycles, right? Because you have low IPC. So this drags out the window. And, you know, as we've seen in the previous slide, reduces the accuracy. So that's why the IPC is actually the worst. But like I said, this is not really obvious at all. Yeah, so the best is just a fair round robin, turns out. Yeah, what do you know? All right. So obviously we get some nice benefits, right? It's all nice and good, but we also pay something, right? We need more hardware, need energy. Yeah, the paper doesn't go into too much detail here. It gives this area overhead of 7.8% for a single core chip, and if you amortize it to quad core, it's about 2%, which is not too bad. Of course, I'm not a computer engineer, but it doesn't sound too bad to me. Also, obviously, the CRE queries the cache as well, right? Because it sometimes needs to fetch memory. And this increases the requests by 35% as they estimate or measured. For energy, they measured in multi-core systems. And the energy is also reduced simply because it's faster, right? You don't execute for as long, so you don't need as much energy. Yeah, the plot is on bandwidth consumption, which you might also be concerned about, right? Prefetching a lot of stuff. But we also see it's actually better than prefetchers, right? Probably because it's more accurate. And yes, you know, very manageable overhead overall. Okay, I think that's all I have for, yes. Okay, so that's kind of the overview of the paper. I have no idea how I'm doing on time. Oh, okay, that's fine. So yeah, first of all, any questions on like the mechanism, on implementation, background, anything? Oh, good, okay. So some strengths, but you maybe haven't read the paper in as much detail. Maybe does someone see strengths of the mechanism, right? Of what I shown of doing this continuous run ahead in this way. Yeah. Yeah, actually, now that I think about a question, I kind of showed you already that part, didn't I? So okay, yeah. So whatever. I'll give you some of my thoughts. What I thought was good about the paper and the idea. So what I'm told, this idea of having like a prefetcher kind of thing in the memory controller is pretty new, at least at the time in 2016. So that's right. It's like a new thing. There's a good motivation of why they're doing this paper, right? What is the problem? Why there's still room for improvement with run-end execution. Then the results we saw were good, and what we had to give up, what we had to pay, basically the cost is not too bad. So it's a good cost to benefit. Then the paper itself really does a good job of backing up all its points by simulations and empirical kind of arguments. And also a bunch of design choices are motivated this way, even though they wouldn't necessarily have to be. And it's also pretty detailed, right? I mean, it's long, but it's also, it doesn't waste any space, it feels like. It goes into many different kinds of aspects of the implementation, tries to be very precise. Okay. Weaknesses. So yeah, weaknesses of the paper, mainly these are, is that I felt like, even though it is very detailed, reading it for the second or third time, I still felt like some stuff is still unclear. And this might be because the scope is kind of big, right? You introduce this new unit, right, that does some optimization, and there's probably a lot of questions to be answered. And yes, I don't think it quite answers all of them. But yeah, maybe just part of the problem statement, I guess. The results analysis is very limited, in my opinion. For example, there's this different benchmarks, and there's sometimes huge differences, but they don't really expand on why. There's different results depending on which benchmark is used, and also homogeneous or heterogeneous workloads. They introduce this notion. They always have two plots, but there's nothing really. There's no insight gained from this kind of division or this distinction. So that was something. Then these limitations and costs that this continuous runahead and the CRE have are very briefly only discussed. This slide I had on cost is actually almost exhaustive. There's not much more. There's like a few energy plots, but that's basically it. So one could have expanded on that. Yeah, for example, in this way, there's no energy consumption experiments for single core. Then also would have been interesting to see like what this thing does when it's not actually used this heavily, right? When it's not memory intensive workloads. Yeah, and also the experiments are all simulated, so it is unclear how close to the real world case they are. Even though there's obviously no way around in this case. You can't just implement it in hardware and find out. So yeah. Any thoughts or maybe questions about these strengths and weaknesses I listed? Maybe some additional ones. All right then. I have two topics for discussion. First of all, this runahead execution, I've shown you what it does now, and you also what prefetching tries to do in general. And I found it interesting to think about how this would conceptually work on different workloads, right? Or like accessing patterns, stuff like that. And also how in these cases we compare this runahead or how it compares to prefetches, right? What the up and downsides are. So I don't know, is the question clear? but can someone a thought of what might be an interesting workload or program or application to look at under this scope?
I mean, one type of workload that I can think of that Runahead would work particularly well on is programs that access memory in very sporadic places without any form of pattern. Because since whenever we stall, we basically execute further ahead with Runahead, then we can load those sporadic memory accesses. But if we had a prefetcher, for example, like a normal prefetcher, they usually they fetch in patterns of some value, and they might not perform as well if these memory accesses are really random.
Right. Yeah. Yeah, that's definitely true. It's much more flexible. Yeah, that's true. Do you know any maybe like actual applications, like any actual programs, like where you might be interested in, where like performance is kind of critical? Because honestly, I have a hard time coming up with one.
I can't think of anything off the top of my head.
Yeah. So this is it's a good point. I put here some more concrete like examples, and maybe something that's close to what you said is like a hashed search. So if we have like a data structure that is hashed and we do a lot of lookups in that data structure, we can do maybe the hash function possibly in this run-end execution, and then load the memory. But a prefetcher, to my knowledge, would have a hard time understanding or prefetching a hashed or index or address, basically. Yeah. So some other cases I put up here is search in general. So for example, linear search. You just have an array and you want to know if something's in there, but you don't have any more information about the array, so particularly it's not sorted. Yeah, anyone see how these two kind of ways to do prefetching would compare on this kind of workload, on a linear search?
Well, I guess in a linear search, normal prefetcher that always takes an offset already predicts every access right. So there's no point in doing any run-ahead execution.
Yeah, that's basically it. Yeah. I mean, linear, like it says, right? The access pattern is very simple, very linear. So yeah, any simple prefetcher even can really make this out and prefetch this stuff. Of course, Runahead doesn't do worse, right? You can still execute it, find the dependency chain, which is actually very simple in this case, and also fetch some useful stuff probably. But yes, you could probably get it done with a prefetcher as well. So something more interesting would be binary search. A little more tricky. Any thoughts on that?
Well, I'm guessing the run-aheads would also have a hard time figuring out the addresses because it is dependent on what value you find at the cache miss. So it's like with a linked list, you can't just know the next link.
Yeah, yes, that's something to consider. Kind of every access is dependent on the previous one. In this way, that's true. Yeah, obviously you have kind of the situation if you do a lot of binary searches on the same array, then a lot of your pivots will be in cache. And then maybe you can, if one gets dropped out, you can maybe with Runahead execution, you can kind of maybe get it. And so the rest is maybe also in cache and optimize something like in that sense. But yes, it's might have a hard time. I agree. And actually, as I'm told, prefetches, modern prefetches can actually detect the pattern here. So they can actually prefetch pretty well in this case. You know, with this access pattern where it, like, you know, split in the middle and then the middle again, this kind of accessing. Okay, well, I guess I'll stop it here, or is it okay if I run over or go over? All right, sure. So the next thing, maybe linear algebra is also not too complicated, right? Thinking of matrix multiplication. Yeah, what are your thoughts on that? I think he was first.
No, that's again probably a case where prefetchers can also perform well, because matrix multiplications are like, you only need to do the next element, and these are in linear sort of offsets, so you can probably find that pattern quite well.
Yeah, that's correct. Yes, pretty much that. Right, it's still kind of all in sequence, the accesses. I think there's, for matrix multiplication, there's one that like jumps columns, I think, or something like that. But still, that's also just like strides. So yes, very much do with a prefetcher. And yes, in the same sense as linear search, Runahead execution can also detect or find a dependence chain that does this as well, but it's not going to outperform prefetcher, would be my prediction. Something a little more interesting again is maybe graph operations or algorithms. So maybe like, yeah, if you think of like adjacency, a list kind of structure, and you want to do operations on like the neighbors of a node, for example, that kind of workload. Do you think that will work well for either of these types of prefetching, or bad or poorly? Yeah, so my thoughts were, this is probably a case where Runahead execution actually has an advantage over a node prefetcher, because it's exactly, this is actually a case where it's kind of erratic, right? The access pattern. Now I think about it. You have your node, right? You have some pointers to other storage to its neighbors. And your operation does some stuff on these pointers, but a prefetcher cannot detect any pattern of how these are in memory. So yeah, this is probably where Runahead execution does pretty well. Okay, so I think I'll close it here. Sorry for going over time. Yeah, thanks to my mentors for their help. And yeah, have fun with the next talk.
So we have the second lecture from Leonard. So Leonard is currently doing his bachelor's in computer science, and he is in his 5th semester. So he took his digital design and computer architecture course last semester, I guess.
No, 1 year ago.
Oh, a year ago, and that made him interested in computer architecture. So here he is. So today he's going to present Pythia. It's kind of similar to what in the same direction on prefetching that you have seen in the last lecture. So you can take it.
Yes, thank you for the introduction. I'm going to be talking about Pythia, a customizable hardware prefetching framework using online reinforcement learning. Let's start with a short outline of my talk. First, I'm going to explain to you what is prefetching. I'll also go into what is reinforcement learning. And then we're going to take a quick overview over Pythia and how it works and how it uses those concepts. Then we're going to evaluate Pythia together and look at some of the key results. And after that, we're going to have a short discussion and I will give some of my own conclusions. So what is, wait, is it the right slide, Rahul? I think reinforcement learning. Are those the right slides? I'm a bit confused. I think reinforcement learning is missing. Pythia updated, I think it should be. Otherwise, I'll go with this. But I can just. Yeah, no, it's not the new one. Sorry for that interruption. The talk outline still remains the same roughly, so perhaps I don't need to repeat that. However, instead of prefetching, we'll start with reinforcement learning. What is reinforcement learning? It's a specific type of machine learning in which an agent tries to maximize a numerical reward and tries to take the correct actions so that he gets the best reward. How this looks graphically is that we have the agent up top. Then we have an environment. The environment supplies the agent with a state that can be multiple different features depending on what you're trying to learn. Then the agent calculates an action or takes an action, gives that to the environment, and after that, the environment gives the agent the reward. This is also the reward we're trying to maximize. So basically, taking the action which maximizes the result. That's the general reinforcement learning approach. Pythia especially uses a specific type of reinforcement learning, which is called Q-value reinforcement learning. It's quite an intuitive approach. How it works is Pythia has a table with all the states, and for every state entry in the table, there are multiple actions, and then for each action, there is a Q-value assigned, which is sort of the predicted reward, and then it takes the action with the highest predicted reward. Yes, so that's Q-value learning. One very famous example of reinforcement learning is AlphaGo. I don't know if you guys have heard of it. Maybe you know AlphaZero. That's the chess engine. Yeah, chess engine, AlphaZero, and that's a Go engine. Go is a Japanese board game. Perhaps intuitively, one could here think of the action being taken as a move on the board, and a good move would correlate with a high reward. And now let's take a look at what is prefetching. We've already heard it in the previous talk a bit. Prefetching is in general the idea of trying to predict what address is going to be needed next. And then we can take it from a higher level in the memory hierarchy and put it at a lower memory so that the access is a lot faster. The reason we do this is because memory latency is high, especially for the big or the high memory levels. The latency is even higher. So if we fetch correctly and put it in a lower level, then we can access the data much quicker. For this to work, we obviously need to fetch the correct address, and we do need to fetch it timely. Also, a topic that was previously mentioned, I think, is the predictability of access patterns. Prefetching works particularly well on address access patterns that are very predictable, because then it's obviously easier to guess which address will be needed next, and then it's easier to prefetch the correct data. One concern one might have when looking at prefetching is, does it affect correctness? So let's say we fetch the wrong thing, can we break our program? And lucky for us, we cannot break our program. We simply have an address in our cache which will not be used. It sits there, it might clog memory, I'll get into that soon, but we do not break the program. Now, what are still some problems with prefetching? First, I want to go over 3 metrics which are used to determine how good a prefetcher performs. There is accuracy, which is from all the prefetches that I issued, how many are actually used, so how many were correct. Then from all the misses, so from all the cache misses, how many were able to stop using prefetching. And then there's also timeliness, so how many of my prefetches were on time and how many were late. The main concern in general with prefetching is bandwidth consumption, because we are using the same memory lane. So what we're doing is we're reading from memory and we're writing from memory. That obviously can clog memory. The good news is that we can use idle bus bandwidth. So when the processor does not need or not read or write from memory, we can sort of chime in and do our prefetching, but that's not always possible. And while we do not break our program with an incorrect prefetch, we do still pollute the cache. What that means is, let's say we have a wrong address, and then we take that and put it in the cache. If the cache was full, for example, we need to evict some address. So we need to evict some data from the cache, and that might actually be very useful data. So we just put something bad instead of something good. That obviously hinders performance. Now, how can we prefetch? There is a bunch of different approaches. Perhaps the easiest one, and also one of the very intuitive ones, is a simply software-based prefetcher. That is, the compiler generates prefetch instructions by itself and then hands that to the prefetcher, and the prefetcher just has to execute those instructions. The problem is overhead, because those instructions that are given to the prefetcher, they're like actual program instructions, meaning we increase the amount of instructions that our CPU has to execute for the program to finish, which is obviously not something good. It also makes programming harder because the compiler needs to come up with these instructions in some way. Another approach is hardware prefetching. Pythia is one of that. So Pythia is a hardware prefetcher. There, the prefetcher just takes hardware states. So instead of taking instructions directly from the compiler, it looks at different metrics from the hardware or one metric from the hardware and then generates a prefetch based on that. The upside of that is obviously that we do not need to bother the compiler that much. So the prefetcher will work on its own regardless of what everyone else is doing. And it makes the programmer's life easier, and we also don't have that much overhead. And in recent times, something that has become more of a thing that might be possible is software and hardware co-design. That is practically like a hardware prefetcher. So it looks at the states in hardware or reads the features in hardware and then predicts based on that, but it also gets compiler tips. So instead of now getting concrete instructions from the compiler, we have tips. So to say, it would be a tip would be, this is an array. And then you can be like, okay, they're all linearly spaced, or this is a random access, then maybe you're not gonna just prefetch at all. And this is more complex because you need to have basically the hardware prefetcher side, and you then need to make the compiler give some tips, but it can provide more accurate results. And we're going to mainly take a look at hardware prefetchers for now, because Pythia, as I said, is one of them. And that brings me right to my next topic, a general overview of Pythia. So Pythia tries to tackle a lot of problems with current prefetchers. And for that, it's maybe good to look at what are some things that many prefetchers currently do not do well. Many prefetchers currently only use one program context info. One example for a program context info is PC, so the program counter. And that's obviously not good because you cannot predict complex patterns if you only have one information to predict upon, let's say. The second thing is that they lack inherent system awareness. There are, let's say, modules you can add to a prefetcher with which it then has some system awareness. System awareness meaning the prefetcher knows roughly what's going on in the system and how clogged memory already is, for example, and then can adapt to that. But Pythia has that built in right out of the box, so you don't need to put any module on top of it, which is obviously good. And most current prefetchers like customizability. Meaning even if I know what type of prefetching my workload may need, I cannot really go to the compiler and say, okay, this time prefetch more in this direction, this time prefetch more sort of that way. But Pythia tries to change that also, or does change that also. How does Pythia change that? Pythia uses reinforcement learning to learn prefetching patterns based on multiple program context information. So instead of the previously one program context information, it now has multiple, and it uses system level feedback. And it's in silicon customizability. So you can change if I know what workload Pythia will be working on, I can change how it behaves. That's obviously something good, especially for an expert audience maybe, who knows how to use this very well. How does Pythia do that? I will pull up a quick comparison to the general reinforcement learning approach. So instead of the agent that we had previously, and instead of the environment, we now have the prefetcher and the processor memory subsystem, but it generally mirrors this. Instead of a state, we now have the feature of memory requests and the address that we're currently accessing. So for example, a feature could again be the program counter. And then the concrete action that we're trying to find, so to say, is an offset from the address A that we previously got. That's, let's say, our prefetch. And then the memory subsystem will assign a reward based on how good our prefetch was. That's the reward in the general reinforcement learning sense. Now let's take a closer look at what a state is in Pythia. It's a k-dimensional feature of vectors. Each feature is consists of control flow and data flow. Control flow examples could be the program counter, the last 3 program counters, or a branch program counter. So if you branch, where do you jump, basically? And the data flow examples could be a cache line address, so very specific line of cache, what address is in there. And then you also have the physical page number, the delta between two cache and address, and the last four deltas. But there are much more. That's just some examples. Maybe to make it a bit more clear, also this would be a state. The left thing is the first feature. This is the second feature. That feature consists of control flow information and data flow information, whereas this only consists of data flow. So you don't necessarily need to have both. You can also just have one. Now, what is an action? As I previously said, it's an offset from our address. But what's the action space? So what actions can we actually take? And that depends on our page size. Why does it depend on our page size? Because we don't want to cross into the next physical page. Why do we not want to do that? Let's say even if we know our program is going to exceed its current virtual page and need an address outside of that, we do not know where that virtual page lies in memory. So let's say even if we predict that we might need something outside of this page, we have no idea of mapping it to our physical page memory. Yes, which pretty much renders it this way that you just need to fetch inside this page, because otherwise it's just too hard to map to the virtual page. And it can also not fetch, meaning a zero offset means no fetch at all. This action space is quite large though. So in order to learn efficiently, we still need to prune it down. That's done by something called design space exploration, meaning we look at the whole design space and then we see, okay, which actions did well, which actions were useless, and then we just cut the useless ones out, meaning we just remove the bad actions by testing in general. Now, what is the reward? The reward defines the objective of Pythia, like I previously said. It encapsulates two metrics. It's the prefetch usefulness, so how good was our prefetch, and it also encapsulates what's going on in the system. That's the inherent system awareness that I was talking about. The main thing that Pythia is concerned with is memory bandwidth. So we're only going to look at that as a system level feedback. One could perhaps also look at something else, but in our case, it is this. There are 7 distinct reward levels. I think accurate and timely and accurate but late are very intuitive. Loss of coverage, not so much, but loss of coverage just means that we have exited our physical page. So it's also a wrong prefetch, let's say. And for inaccurate and no prefetching, we have 2 different levels. That is with low memory usage and with high memory usage. What's the upside of this? The upside is that, so why do we have these levels, so to say? The thing is, if memory is highly contested, so if the memory is always being used and the system needs that memory lane, a bad prefetch is really bad. So we want to punish an inaccurate fetch very harshly. However, if memory is readily available and the program doesn't read memory at all, we can just fetch. And if we fetch wrong, so be it. But we didn't really bother anyone, let's say. Same as with no prefetching. If memory is very highly contested, we might opt to just not prefetch if we're not sure enough. And whereas if memory is not that highly contested, it's generally just a bad idea to not prefetch because you're not losing anything with a wrong fetch. These values are also set via automatic design space exploration. That's the same thing as with the states. We just, by testing, pretty much figure out what's the best values. And that's the in-silicon customization that I was talking about. These reward values can be customized. So you can go into Pythia and say, okay, for this, for accurate and timely, give this reward, for inaccurate, that reward, and so on and so forth. How does Pythia do that in hardware though? So how is it actually implemented? We have the queue value store over there that I previously mentioned, and we have an evaluation queue. Those are just the last couple of prefetches, so the last actions that Pythia took, so to say. And whenever there is a demand request, so memory access, let's say, we do 2 things. First, we generate the state vector, which is then used to look up the QV store, which is then in turn used via just maximizing the reward value to generate our prefetch. And we evaluate our previous prefetches. meaning we look at, okay, did we actually prefetch the address that I wanted to access, or did we not? And then we can evaluate, then we can assign a reward based on that to the action in the queue. As I said, it then takes the max, and then it generates the prefetch and gives that to the memory hierarchy. After that, we insert our action as a state action pair in the evaluation queue. And then when we have the reward assigned here, we then put it back into the queue value store and sort of calculate a new reward so that we can predict better. That's where the learning is. This part is where the learning is going on, let's say. That's the important part, is by evaluating the old actions we take, we can then make better queue values. And for being not timely and timely, there is the prefetch fill. That's just, was it timely or was it not timely? That obviously also has an impact on the reward that we will assign. Previously, yes, sorry.
I was a little curious on the details of the queue value store. If we store this action state pairs as a matrix, from what I see in the image, then the size of it would be 127 times 2 to the power of k, which I would imagine is quite big. So is there any efficient way to store these, or?
Yes, and Pythia does not store it exactly in that matrix. So what Pythia does is we break each queue value up. So we break it down by sort of the individual features. So for each feature, we then have a corresponding reward, let's say, or a partial reward. We maximize, so for each feature, we then maximize the partial reward, and then we sum them up, and then we get a reward for the whole action. So it makes sense? And then you just max, so it's pretty much 2 maxes instead of 1, and then you maximize over all the things you summed up, you then max again to get the best action.
Yeah, that makes sense. Thank you.
That's a great question, by the way. Any other questions? Maybe if we had one. Anyone else at this point? Okay. No. In the title, there is something called online training. I quickly also want to discuss what is online and what is offline training. Online training does not mean Pythia connects to the web. I was previously confused. It means it's learning while working. Whereas an offline algorithm would not do this. An offline algorithm is pre-trained, and then it's sort of shipped out of the box and doesn't get better, whereas an online algorithm does get better over time. The goal behind online training is that maybe at the start, you do not have the best results, but over time it gets better and then surpasses how good an offline training can be. And one can combine the two. Obviously, an obvious way of combining the two is we pre-train, use these values as a start, and then start learning from those. That might make sense in some cases. Now let's go over the performance increase of Pythia. That's 3 state-of-the-art prefetchers. And that's Pythia. What you can see is that it beats every state-of-the-art prefetcher in all core configurations, but the difference is much more noticeable when the cores are high, and this intuitively responds to this system awareness that I was talking about. So because the memory is more contested. Yes, it beats them in all core configurations, but when the core counts are high, they're even better. Pythia is open sourced. It's artifact evaluated. All the traces are public. Traces meaning what it was tested on. Yes, that's a great thing, let's say. Yes, and that was my short presentation over Pythia. I will now also tell some strengths and weaknesses, and then we can get into the discussion. But at this point, I wanted to ask, are there like any questions regarding how Pythia works, regarding reinforcement learning, prefetching? all clear, then we can move on. So what are some strengths of Pythia? The performance is obviously great. We saw that in the previous graph. It is a pioneer in using reinforcement learning and prefetchers. It was one of the first papers, even though it was released just 2 years ago, so that's not that old. And the in-silicon customization is a very cool feature, I think, and it can be very great, especially in more expert or more important or complex workloads, let's say. However, the main weaknesses of Pythia is that even though I previously mentioned the whole efficiency thing, and you quite right pointed out that this would be huge, even if they do something clever, it's still quite big. It's 25 kilobytes large. That's the same size as an L1 cache. So the smallest cache, it is large, let's say. And also changing rewards. In your usual Intel 13700, like, no end user is going to go into your prefetcher. So that's only really an upside for maybe cloud computing or something else. And one of the bigger problems I also found was that the computation overhead is not addressed. One may ask, what does Pythia need to compute? It's the new Q values. So this is the predicted Q value, and that needs to be computed in some way. Those are all floating point number multiplications, floating point number multiplication. So that's floating point number multiplication, addition, multiplication. Those are expensive. So floating point multiplication units are expensive. And that's also what I want to start my discussion with, is how would you go about solving the whole computation issue? So how would you compute the values? I have 4 ideas. It's stealing CPU circles, so just use the CPU, floating point multiplication units, or maybe we can try the learning algorithm with a cheaper way, so with integers, and then just use an integer multiplication unit, or maybe someone has a completely different approach. So which one of those 3 would you prefer? Or
I think that a low precision floating point multiplication unit would be the best thing, because you probably won't get a good result with integers, but with floating points you can always adjust the size, and you can figure out what you really need, and then you can optimize for that.
yes, sounds like a possibility for sure. Any other ideas or opinions? Someone want to use the CPU cycles? So does anyone think that stealing CPU cycles is the best idea? No, not really. Okay. Yeah, I also I would agree with you. I think that using integer multiplication unit, or you'd obviously have to look at it how good you can learn. Also using cheaper floating point multiplication unit, you'd also still need to look at it. Okay, does it still work as well? However, stealing CPU cycles is, what you're doing is you're using the CPU for your prefetching, but the prefetcher wants to help the CPU and not hinder it. So you're kind of defeating your whole purpose in the worst case, right? I mean, you could use idle time, but in the worst case, you'll end up just adding a bunch of computations to the CPU, and it's busy with your computations instead of actually running the program, which is kind of the worst case, let's say. So you'd certainly need your own multiplication unit. At this point, I also want to show you something that I found very interesting. This is a completely different approach, and while they do not go into much detail about the computation, storage-wise, they're much better. It's called MicroArm Bandit. It came out 2 weeks ago, so it's very new. And it only uses a couple of 100 bytes of storage, which is a huge increase over 25 kilobytes. The way they do it, quick and short, is they use a completely different reinforcement learning algorithm. They use a multi-arm bandit, which drastically reduces the number of states or actions. Let's say actions you can take, not states. if you know this Vega slot machines, that's why where the name comes from. What the algorithm can do is it can pull different levers, and those are all different states it can take. But there's like 8 or 10 different states, which obviously makes it much cheaper than the previous state action pairs. I also wanted to ask you about the online and offline question. Maybe Pythia uses online learning. Do you think online or offline learning is better? Would you combine them? What do you think is best?
When it comes to offline, unless you have probably one of the most extensive data sets ever, it probably will not work very well due to the fact that there are so many different workloads in just an average kind of like computer that even if your data set is massive, you will most certainly miss at least something. And then kind of the entire purpose of the reinforcement learning will be defeated because you cannot adapt anymore. So I would definitely, if I were to pick between the two, I would definitely advocate for online, but a combination approach would also be very interesting, I think.
Do you think a combination approach would be better than just simply online learning?
I think it could be better, but it's also a bit of a complex issue because you need to first figure out how to adapt them. You might train it. I mean, you can train your model first and then have it adapt, but I would imagine that also takes quite a bit of time for the training offline. I think the issue just becomes a little more complex, but it would definitely be better, I'd say.
Okay. Any other opinions? Maybe someone advocating for offline learning? The huge data set is best. No.
There's a question on YouTube. How does Python code get converted?
How does what?
Python code get converted to
Question on YouTube. Okay.
So there's a question on YouTube, maybe related to the implementation of Pythia. So how does Python code get converted to machine language? Not sure.
Python code.
Is Pythia implemented in Python?
No, it's implemented in Gzil. I
think it's not relevant. Yeah, it's not a relevant question, but
yeah.
So
what's the question?
So, I mean, this can be a good discussion point on how Pythia was evaluated.
Yeah, I think this is, I'm not sure where exactly this question is stemming from, right? So the question is that how does the Python code is converted to machine language? But maybe the question is coming from the fact that, okay, how exactly this is implemented, right? So we have implemented this in purely in C++ with our simulation environment, right? But then that does not, let's say, yeah, I mean, that also leaves a possibility of, using traditional frameworks like what we have for, let's say, OpenAI Gym or any traditional frameworks that we have publicly available, reinforcement learning models to train. We can probably use those frameworks also, frameworks also here. Eventually, to show that the hardware complexities that we have involved in Pythia, like what the question that you asked, right? That how exactly the Q value stored in storage is implemented, because naively implementing the Q value store is going to be huge area over it, right? Like it's a big table. So to see whether the implementations that we had is going to be useful to implement inside a processor, and how, let's say, big of the area is going to take, what is the frequency that it can be clocked at. We have also implemented Pythia in Chisel. So Chisel is something like a hardware descriptive language. You can think of it as a synthesizable, hardware kind of thing. So yeah, so we did that analysis there. We found out that okay, Pythia has like small area overhead as compared to the traditional big core like area footprint. As well as we also got some sort of feedback that Pythia can be clocked at certain frequencies which we expect a prefetcher like Pythia would need to operate on. So that gives us some feedback, that confidence that if somebody wants to implement Pythia as is without any optimizations further, it can still be implemented. But then we have also, like recent works that is showing that we can further reduce the area overhead while keeping the performance improvement same. So yeah, that's that.
Yes. It's my
No, not the question, but you were asking if someone could advocate for the offline Pythia strategy, but I might not be the best example, but for example, if we have a graphical processing unit that performs only certain operations on neighboring pixels, let's say, if we have basically just a data set of these basic instructions that work on neighboring memory or like on neighboring memory locations, let's say, then training Pythia like that, and then just using it from the start as an offline based reinforcement learning algorithm could work pretty well, because we basically limit the amount of different instructions we do inside of this processing unit. So if we know that we have very limited instructions and they don't vary a lot in like the range of memory that they access, then the offline could be much better and also slightly less computationally intensive than the online counterpart, let's say.
Yes. But yeah, I agree with you. In general, maybe offline learning is something you could look into if you know what kind of workload you're working on very well, because then you can just pre-train on workloads that are similar to that. So you have the perfect values, let's say. In the ideal case, obviously they won't be perfect, but you will be very well adapted to what you will be facing. That's definitely. Also, as you said, computation overhead, it takes time to pre-train. So it needs to be an important task. Like you're not going to, for any talent, you're not going to pre-train a huge workload for just any small task that you don't care about. Yeah, we pretty much already went into that. I think combining them seems like a very good approach as well, though, especially if we're thinking about, for example, your average Intel CPU, because you have the resources to pre-train on a good workload, and you have the time to pre-train well, and then your processor just starts out better. And with the online learning, it can get even better. I also, and that perhaps ties into the first question.
Yes, I'll make a comment here. So regarding the training time and let's say the time it takes to start making better decisions from the get-go, right? So yeah, I mean, in our evaluation, we do see that even if we have very small warm-up, so this is what we call warm-up phase, right? So we do a simulation after certain warm-up. So the warm-up is essentially going to, as the name suggests, it's going to warm up the CPU, right? So the structures, the learning algorithms, everything that is going inside. And then we have the actual simulation phase that finally we profile, right? But this sort of approaches might be, let's say, not the optimal if you go for more like emerging processing, not processing, let's say emerging computation paradigms. Like for example, have you heard of function as a service, right? So So these things are like very small, let's say, like a piece of code that is executed in server processes. Okay. So it's like you are only going to pay for executing a function in a cloud server, and you're only going to pay for that time that it takes to execute that function. You're not going to execute the entire application. You're not going to even load a VM and then run the application. This is just to like reduce the cost of the end user in the end, right? But then that also adds different sort of challenges for us as an architect, right? That then you all of a sudden have this sort of paradigms emerging that you're only executing a function, which is barely, let's say, a few millions of instruction, right? That might be even not enough if you go for online learning. So in those cases, maybe offline learning, or maybe let's say cross-training across the functions, right? That saying that, okay, I have seen this sort of function before. There I have learned this sort of Q value. Let's restore that Q value state again when you see similar functions again. So maybe those sort of approaches might be also useful. That makes sense?
Yes, makes a lot of sense. Any other comments? The next thing I wanted to ask is where do you see this prefetcher making sense? I think also you just mentioned cloud. Maybe you can also think, okay, could we use this in cloud? Could we, yes, could it be more useful in cloud than in personal computers, or just some other applications? This prefetcher. It's quite expensive, but good performance, let's say.
I'll just ask a simple question, and if it's really the most accurate prefetcher, I think we would already implement it in our systems, right?
Depends on how high the overhead is, right? Like
correct, yeah.
The computation overhead, as I previously said, is a big problem. Maybe that's just too big. But yeah, obviously there is a point where it's so good that you need to use it. But I think in this case, it does provide good prefetches, but the computation is probably too expensive. That's kind of what I caught. I don't know if that matches what makes sense. Okay, so no applications for Pythia. I thought about some. One thing that I think could be especially interesting is maybe something that Rahul also pointed out before is in cloud. Maybe not just cross-learning about using a certain function again, but also maybe multiple processors could learn together, or maybe even multiple machines. Maybe you could have one shared Q value table. Obviously just an idea, but that could be very interesting to learn even faster because you just have a bigger data set. Other than that, yeah, mainly for an expert audience. Also because the in-silicon customization just makes more sense there. And yeah, what I meant by inside SSDs is in reinforcement learning. We also saw, like, I think it was 1 week ago, it's currently also used in SSDs. And in SSDs, I think they're also more complex. You just have more storage space. 25 kilobytes is a big problem on the computation unit, but maybe not so much inside an SSD. And then I think one of my last questions is, I showed you the different types of prefetchers. Again, this is where Pythia is. Software and hardware is the very complex one, which uses both of the paradigms. Then there is, I just categorized it as reinforcement learning or machine learning in prefetching. And the stride-based prefetcher is, I think, what was mentioned in the previous presentation as well. It just guesses a fixed amount and tries to figure out a stride, which is like, I don't know, like +8 times n or something. And then it just continuously uses this offset, but does not change the way it approaches the offset. Which of these do you think is maybe the most promising for the future? And which of these do you think is maybe the best to use right now? Or
Well, I mean, it really depends on what you want to do with your, or what programs you're trying to run. Because, for example, as we mentioned earlier, if you have, in the previous presentation, for example, if you have a linear algebra-based library with whatever operations you're running, a stride-based prefetcher would do the job almost perfectly at a much lower cost than the approach we saw right now. But if you really need the flexibility in your program to be able to adapt on the fly, machine learning seems like also a very good approach to basically just adapt to any kind of workload.
yes, makes sense. Anyone else with comparisons between the types of prefetchers or some ideas? Maybe I could also ask, do you think machine learning is future? Is like maybe the future of prefetching? Do you think this is a viable approach? And do you think it will get even more viable, or? Not really, no machine learning, no machine learning for prefetching. Yeah, currently most prefetchers that are being used are stride-based prefetchers. Just a quick information. I don't know what Intel is using, they don't disclose that, but most prefetchers are stride-based because they're cheap and they provide good values, as you said, in matrix multiplication, arrays. There are many different cases where a stride-based prefetcher is already quite good. And I think hardware prefetching seems like a good trade-off currently, but I do think that maybe as prefetching and as computation power becomes more cheap and the storage maybe also becomes cheaper, maybe reinforcement learning will get even more attention and will become even more promising, let's say. Yes. Where else do you see reinforcement learning or machine learning in general applied in a system? Worried about storage, maybe GPU or perhaps even cooling? Do you even think it's a good idea to like merge reinforcement or machine learning with computer architecture, or do you think machine learning does not belong inside a computer? Say.
Well, I mean, kind of borrowing on the point you made in the last slide about machine learning, right now I feel that it's a very good method. It's mostly accurate. It can adapt really quickly. It's flexible. But the main issue that I see right now is that it's way too expensive to be implemented into actual architecture for the benefits that it provides. Basically, it is very good, yes, but the margin between machine learning approaches and the current approaches we have is not big enough to justify how much more expensive it is to implement them in hardware. And I think this would go for basically most of the computer architecture part, with the exception of maybe storage, because storage is readily available.
Yes, makes sense. Any other comments regarding machine learning in computer architecture?
I would have some comments here. So machine learning in computer architecture. So there are other applications also, like where I can give you, let's say 2-3 good use cases, right? So one use case is, so there is something called floor planning in chip design. So floor planning in the sense that you have, when you're designing a processor, or let's say a GPU kind of a big, for area footprint chip. So you have different components, and then the problem is that how would you place each components to meet certain constraints, right? So first constraint would be the overall area size would be as low as possible, as well as you also need to meet other constraints, like for example, length wire, right? Or like wire length and then transmission delays and all those things. So Google and I think NVIDIA, they have like produce some results, right? So where they have shown that they have used reinforcement learning for automated floor planning. And the key result is that what typically takes, let's say, a month of expert chip designers who knows how to floor plan, that's their job basically. So they can achieve that same expert level floor planning efficiency using reinforcement learning. So this is not exactly, yeah, I mean, people have all.
There was a Nature paper on this from Google and it got retracted after a while, right?
I'm not sure whether it's retracted, but definitely there is another paper which says that they tried to reproduce the result and they couldn't reproduce it as best as possible. So yeah, I'm not sure whether it retracted, but at least it shows that there is maybe some possibility over there. So it's not exactly, let's say, computer architecture as you see it. It's not inside the hardware, but at least it's aiding the design of the hardware, right? So that's one thing. The second thing that people have also used it is that on the server side, let's say, think about Azure cloud systems, or let's say like Amazon clouds, right? So they have multiple different types of underlying processors, right? So one processor might be, let's say, small and lean cores, right? Another processor is much more beefy processor, which is very good for handling, complex tasks. So similarly, you can also think of having machine learning accelerators, right? So like one accelerator is specific for design, let's say handling maybe convolution heavy task. Another accelerator is more useful for LSTM heavy task and stuff like that. So once you have heterogeneous systems like this, so people have also come up with a reinforcement learning based algorithm to map a given machine learning model. If I give it to you, what would be the best underlying hardware to run it on? So to make that decision online, getting the feedback from the system itself is what people have used reinforcement learning on. But yeah, I mean, it's not exactly as, let's say, inside the processor, but still it's aiding somewhat the processing, right, to make the processing faster. So yeah.
Yes. Very interesting. Yeah, I think for offline learning, even more so, maybe there is also many benefits. Maybe if a company deems it worth it to use machine learning before shipping it to production, that is also probably feasible now, let's say. Was also something, storage, as you previously mentioned, that's also what I think is also maybe right now a good idea where you could do online training. And what I think, what I've heard is that GPU scheduling in the cloud, there is some machine learning going on. It's not reinforcement learning, it's some neural network fancy stuff. And in general, I think in cloud, there is probably a lot of ways to use machine learning because you're working on huge workloads. The machines are extremely expensive. Yeah. And probably also some more. Yes, that's it from my part. Sorry for taking longer. Yes. And a special thanks to Rahul, who chimed in, and he's my mentor, and also Ataberk Olgung.
So we would have the quiz on probably open by now, right? So just go back and then definitely do the quiz, and all the feedbacks that we have to produce, just to give the feedback. Thanks again, Leonard. Yeah.